I0.1 electrical linear actuators. Of the three types of linear actuators, electric, hydraulic, and pneumatic, electric actuators require the least hardware and maintenance. However, they tend to be relatively slow moving or have other restrictions, which makes them suitable in only a limited number of applications. For example, electric actuators work well for lowering the landing gear in an airplane, but could not be used for a spray painting robot, which must make quick, long sweeps. A lead screw actuator has a threaded shaft, called the lead screw or drive screw, which is rotated by an electric motor. A nut on the shaft moves in a linear motion as the shaft rotates. Figure I01 shows a diagram of the electric linear actuator. Notice that the rotary torque of the motor is transferred through a gear train to the drive screw. The output motion results as the nut advances or retreats along the threads, depending on which direction the shaft is rotating. Note that the nut must be constrained from rotating. To reduce the friction and increase the efficiency, many units use ball bearings to transfer the force from the drive screw to the nut. Figure I02 shows a cutaway diagram of this design, called a ball bearing screw. When the shaft rotates, the balls roll in the grooves. When the balls get to one end of the nut, they are recirculated to the other end through small pipes. Ball bearing screws practically eliminate friction when compared with the traditional nut on thread design. Figure I03 shows a cutaway diagram of a practical electric linear actuator. The unit resembles and acts like a hydraulic cylinder, the main visual difference being the attached electric motor. Many units come with a built-in electrically activated brake that prevents the shaft from rotating when the motor is not energized. This feature ensures that a heavy load cannot backdrive the motor after it is turned off. Also, over-travel limit switches should be included in the application design to cut off power to the motor if it attempts to drive beyond its intended travel. Electric linear actuators come in all sizes, with rated loads from under 100 pounds to over 1,000 pounds and strokes from 4 to 36 inches. An important parameter for electric actuators is extension rate, that is, how fast a unit can extend and contract. A typical extension rate is around 1 inch per second, but this depends on the size of the motor and the load. However, even the larger units are no match for hydraulic cylinders, which we'll cover in the next section, when it comes to speed and power. The electric actuator is characterized by slower, steady linear movement. These graphs show the characteristics of a 12-volt linear actuator. Notice that as the load increases, the extension rate decreases and the required current increases. For applications that can tolerate the slow extension rates, the electric linear actuator has some distinct advantages over hydraulic and pneumatic systems. Specifically, electric actuators require only wires to be connected, not tubing, do not require extra supporting hardware such as pumps and tanks, use power only when they are actually moving, and compared with hydraulic systems are less messy. On the other hand, compressed air for pneumatic systems may already be available, and for working around explosive gases, a non-electric actuator would be safer because there's no sparks. Electrical lead screws are relatively slow moving. A solenoid is a simple electromagnetic device that converts electrical energy directly into linear mechanical motion, but it has a very short stroke, length of movement, which limits its applications. The solenoid consists of a coil of wire with an iron plunger that is allowed to move through the center of the coil. Figure A shows the solenoid in the unenergized state. Notice that the plunger is being held about halfway out of the coil by a spring. When the coil is energized, in figure B, The resulting magnetic field pulls the plunger to the middle of the coil. The magnetic force is unidirectional, so a spring is required to return the plunger to its unenergized position. Two practical solenoids are shown here. The main limitation of the solenoid is its short stroke, which is usually under an inch. Still, there are many applications for short stroke linear motion. Examples are activating electric car door locks, opening and closing valves, and triggering mechanical latches. Most applications use the solenoid as an on or off device. That is, the coil is either completely energized or switched off. However, variable position control is possible by varying the input voltage. Both AC and DC solenoids are used, the major difference being that AC solenoids use a plunger and frame made from laminations instead of solid iron. Laminations are thin sheets of lacquered iron that are riveted together to form a frame and plunger. Laminations prevent power-consuming eddy currents, which are induced by the AC, from circulating in the metal parts of the solenoid. The laminations can easily be seen in Figure B. Table 10.1 lists various models of solenoids. Note the various coil voltages and whether the unit can be operated intermittently or continuously. An intermittent duty solenoid is designed to operate for a short time and then take time to cool. The problem is that, like relays, it takes more voltage to pull in the solenoid than it takes to hold it in the retracted position. Thus, if a solenoid is left on, it is drawing more current than it really needs, and it tends to heat up. A continuous duty solenoid is designed to deal with the heat, so it can operate all the time. The lifts and stroke data in Table 10.1 tells us the maximum pull force, which occurs when the plunger is retracted. The minimum pull force occurs when the plunger is extended. For example, the unit on the first line of Table 10.1 exerts at least 8 ounces of force for the first eighth of an inch of stroke, but falls to 2 ounces of force when the solenoid is extended to its maximum half inch. One of the newer types of linear actuators is the electric linear motor. Basically, a linear motor is a rotary, brushless DC motor that has been rolled out flat. Linear motors convert electrical power directly into linear motion. They are capable of high speed, up to 10 meters per second, high force, over 1,000 pounds, and long travel, up to several meters. And like a BLDC, they have no sliding contacts but do require an electronic drive unit. A linear motor consists of two parts. The base unit, known as the magnet way, which consists of an iron plate with a row of alternate pole permanent magnets, and the moving part, known as the slider, which contains the coils. The slider is supported on linear ball bearings so that it can slide along over the magnet way. There is a small air gap between them. A flexible cable connects the slider to the drive unit. This diagram illustrates the operation of a simplified three-phase linear motor. Note that there are 3 coils spaced over 4 magnets. To start the motor, coil A is switched on, causing it to become a north pole. The attractive force between the north pole and the nearest south pole on the magnet causes the slider to move to the right. When the slider has moved, coil A is switched off and coil B is switched on, causing renewed attractive force to the right, and the slider moves further to the right. When the slider gets to the new position, coil B is switched off and coil C is switched on, causing the slider to move to a position further to the right. The coils have now advanced one full cycle. They are now back to the same orientation as at the start, and the whole sequence starts over. As you might imagine, moving the slider in steps tends to cause a jerky motion known as cogging. Cogging is more noticeable at lower speeds and can be greatly reduced by proper shaping of the coil drive currents, which we'll deal with in the next slide. Switching the coils on and off at the right time in the right sequence without brushes is called electronic commutation. For this example, electronic commutation could consist of 3 Hall effect sensors mounted along the slider, each one controlling power to a coil. The Hall effect device detects when the slider has physically moved to the next position and signals the drive unit to energize the next coil. An actual linear motor would probably be operated in a bipolar mode, wherein each coil becomes alternatively north and south, and 2 of the 3 coils are on at the same time. This system produces smoother operation with more torque, but requires a more complicated drive unit because current reversals are necessary. Figure A shows one schematic for a 3-phase bipolar linear motor that permits the current in each coil to go in both directions, allowing it to be either a north or a south pole. The 3 push-pull amplifiers, Q1 and Q2, Q3 and Q4, Q5 and Q6, should be driven by 3 waveforms shown in Figure B. These waveforms would be created from the Hall effect sensor outputs. Notice in Figure B that the voltage peaks in a sequence A, B, C. This would correspond to energizing the coils as a north in the sequence A, B, and C. Using sine waves to turn on the coils causes the force to be passed gently from one coil to the next and practically eliminates cogging. There are 2 basic designs for linear motors, the iron core linear motor and the ironless linear motor. Iron core motors are more powerful because they have coils wound on steel laminations to maximize their magnetic force. However, in addition to the linear force, they also generate a strong attractive force between the slider and the magnet way. This attractive force is typically 4 times the linear force, so a motor pulling with 100 pounds is pushing down on the magnet way with 400 pounds. The ironless linear motor has no iron at all in the slider, just copper wires embedded in an epoxy strip. These motors are inherently weaker even when 2 sets of magnets are used in the magnet way, but they have small mass for quicker acceleration, no cogging, and no attractive forces. Linear motors are almost always used in a closed loop system, which means they need some kind of linear position sensor to feed back the position. A common and accurate type of linear position sensor is an optical encoder. It's similar to the optical shaft encoder rolled out flat. The components of this sensor are a yardstick-like strip marked with fine vertical lines or slots fastened to the slider and a photosensor mounted to the base. In some cases, the linear motor uses the position sensor data for electronic commutation, eliminating the need for Hall effect sensors.